humans. Welcome to another episode of Teach Jenn Tech, where we have Ben back again. And I'm excited because we are learning the basics of data because, well, use data day in, day out to just watch this stream, hear this stream, do anything about on the interwebs. It all uses data. And Ben, I feel like I should know a better introduction for you, but you're Beth Gamble that does absolutely everything, and currently is a DevRel at Ivan as well. But what's your official introduction?
So these days, I mostly go by the open source technology sommelier, which is kind of as a joke based around my job mostly being about pairing some Kafka, some Postgres, and maybe some cheese in the middle. And the
Okay.
idea of basically trying to pair the right pieces of software to build out a stack. And the reason about this is that these days, most of what you do is no longer just that single column of tech of your server, your database, and maybe a web framework on top. These days, there are more bits in the stack. Therefore, you've got to pair the right pieces together to get the best outcome.
Yes, yes, all of that, all of that.
Also, it's a good
And
joke.
and I feel like that's such a good thing because as I've been learning about databases, especially Postgres right now, a lot of it is I'm seeing how much it's interconnected with everything else. Everything is
Yes.
connected. It's just learning what they are and how they're connected, which has been fun and annoying.
The deeper you get into this, the more you get this kind of weird dichotomy of everything is different, but everything is the same. But it's all very different, but it's all the same, but it won't talk unless you really make it.
And this is something that I've been realizing with learning live in the last 9 months has been things that are very, very complex can make total sense until you go to do it. And then it doesn't make sense at all. And you're like, what? 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 So that is what I have realized that I get really stuck with. And I have linked in the chat, y'all, the playlist from that I started about this series, which currently just has our last episode. Eventually, I will also link in the Postgres ones because they're also learning about data. Yet, anything you want to go over before I show you recaps of last week and where I got stuck?
I think that's really everything. Really, to be honest, other than the playlist is great, please watch it.
Yes, yes. And I feel like so yesterday I had a friend on, his name's Anthony Campolo, and he was on and he works for Edgio, which is a part of Limelight. And I had no idea that his friend Scott was a part of them until they started saying that their Twitter space every week is a part of Edgio. And I was like, oh. Anyway, all of that to say that Scott is the best at doing his radio ads of make sure that you follow everybody on the screen and in the Twitter space and to like, follow, and interact and make sure to come on stage and ask questions.
You really ought to get him to record a soundbite for this and then press the button.
Oh, that, yes, yes, that is what I should do. And okay, well, going to our lovely data spreadsheet, which y'all, Ben did a lot of this work before our stream last week, and I copy and pasted and wrote notes about some of it. So I'm going to go through and see what I remember and get corrected on some things. So if I zoom in, see, this is where we started when we were talking about how data progresses, which and the speed of progression. Where, like, when you have a cache, it's the very, very first part of where data starts. It's only in the single digits of megabytes. And we talked about how 1,024 megabytes go into a gigabyte. Oh, I almost feel like I want to go over here. We're gonna postpone just a moment because would this help knowing the rest of them going through this first, or does this
So
make it more
I
confusing?
so this is really about speed. So this is like this is where so the best thing to do is actually start where we were, and I'll if I think I can run the quick recap as well. So if we go
Okay.
back to where we were, the main
Oh,
thing to do
wait,
is
wrong one.
start.
There we
Yes.
go.
So so the best to start here. So the key thing to start with is the CPU in your machine can only act on a few bits and pieces at once. Those which are the bits in the cache, which is both the fastest and the most expensive piece of memory. When you need more data, you pull it from what's known as main memory or RAM, random access memory, which is nowhere near as costly and is normally a separate chip on your machine through your CPU. And that's kind of measured in like gigabytes. You have gigabytes of RAM. You can go up to terabytes of RAM just about these days, but you're going to be paying like AWS a lot of money for that. Cache is single digit megabytes to about 30 megabytes on a big CPU. You don't get much cache, and it's very, very expensive to get more. So then as you go down again, we get to your kind of persistent storage, because RAM is still what's known as volatile. If you turn the machine off, it's all gone. And these are where you get SSDs and hard disks, the old spinning platter drives. And these are not slow by any stretch of the imagination for what comes next, but they are much, much slower again, but also much, much bigger than RAM. After we get to the disk drives, we kind of go beyond the size of what one machine will hold. And this is where we get to this kind of like what often is referred to as like cloud scale stuff. So we go, okay, so our local area, we might have like 4 or 5 machines all stapled together using the local area network, LAN. And that will give us all the different disks attached to all the different machines to access. That's great, but now if you imagine that cable's going machine to machines, and now your band is now your kind of finite max speed is, I've got a call over there. It's physically further away. It takes longer for the data to get there. It's not that slow by comparison to the next step, which is the wide area network, or the WAN, which is I want to use S3 or equivalent, or some of the block object storage, which is no longer on machines you probably own, but it is if you own them on-prem. But they're so far away by comparison. There's so many of them that it's, once again, much, 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 much bigger. You can store, exabytes of data in S3, but the access speed is going to be commensurately lower. There are some good trade-offs and bad trade-offs there, but it's so cheap by comparison to your cache or your RAM or even your local hard drives that it is very much worth the trade-off if that's what you can get away with. The kind of really important thing to know is that eventually, if you want to act upon that data, it does have to hit your cache at some point, or your CPU can't touch it. This is like if you imagine a production line, like the machine itself has like where the thing that stamps out a punch into a piece of flat metal. That bit we can act upon is your cache. It's a very small area, but then lots of bits can go through. So you got to pump them through the cache to get things done. And that's kind of the core of what we started off with. And that's why we had the kilobytes, megabytes, gigabytes, terabytes, and petabytes. It's just kind of like, as you go down, you get bigger, cheaper, and slower. As you go up, you get much more expensive, much smaller, and much, much faster. And this is where we then jump to that lovely little diagram about latency, because this is like where it ends up being important. Because latency is just the time it takes for something to happen, right?
Yes.
Yeah.
I ended up somehow merging some of the notes, but I'm moving this over so we can see
So that's
both.
the other, the other direction.
Because buffering did help when you were talking about the water.
Yes.
So these are my lovely graphics to go with it. Now, one thing that helps for me to remember when I'm looking at these is for some reason, some words just don't click. Like that
Yes.
RAM and memory are the same thing.
Yes.
Why? I have no idea.
Random
But
access memory.
so I wrote it out.
Yeah.
And CPU and GPU is similar.
Yep.
But do most computers have both, or does the GPU use or is inside of the CPU?
So these days, they are nearly always discrete pieces of silicon. However, they might be built in. You can get a GPU chip is often built into a CPU. So Intel have what's known as integrated graphics often, and those are integrated into the actual same piece of silicon. But they'll still be a separate area, but it'll be as the GPU, but it will be integrated onto the same piece. same wafer, or die as it's often known. AMD do this as well with their what's known as APU range of processors, but it's both. It is not uncommon. It is increasingly common in some places and uncommon in others. When you get to specialist hardware, as in hardware which has performance characteristics, you tend to have discrete units. So there's a discrete GPU, because then you get all of the usefulness of lots of space and good heat management. If you imagine you wanted to have a beefy game running high speeds, you don't want to have all the heat that generates in the same place as your CPU, because you can imagine the load is a lot higher.
That makes sense. So thank you for those clarifications. That does help. Okay, now I have to.
Only one kind of thing to make is like, as you go in, as the problem ends up being that a lot of what we kind of consider computers to be is still based off a bunch of kind of thought processes left over from the kind of late 80s to early to late 80s of I would call the PDP-11 era of thinking.
Okay.
And what that means is all of our various kind of like mental models, often the way we actually program, are based around a bunch of these computers that no longer exist, right? Back when it was so prohibitively expensive to do some things that decisions were made. Though what that really means is, as you come to kind of today's actual like chips and hardware design, so many things are, it depends out the box now. Because I could tell you about like specialist pieces of hardware where they're mostly GPU, a tiny bit of CPU. You could literally like get something called an FPGA, which can then just put all the different bits in one piece of silicon and do all kinds of nonsense. But it basically is because we've gotten so good at building hardware in some respects that we've specialized, like, and then generalized and specialized and generalized a couple of cycles over. So everything is sort of like become that weird, like if you imagine all the dog breeds turning into mongrels, that level.
Okay.
So it's gone a bit strange over times, but I'm still going to go by the generalities we normally use because they still hold true more often than not.
Okay. And that is making sense. Like everything you're saying there makes sense. I now get why you were saying to go to this second. So
Yes.
thank you. Like, so it does say.
So this is like nanoseconds to start with.
Yeah. So I guess the other part that, and this is a big reason, I'm super glad that we're doing this again, but also that I'm writing notes as we go.
Yes.
Is I've realized it's helped me learn so much better. Because people can fact check what I'm actually writing down.
Yes.
It's marvelous. So when we're talking about 1NS, this is what cache is using.
Yeah, so a cache, so the first one there is that the L1 cache reference is half a nanosecond. This is about one CPU cycle. This is like, I can't remember how many CPU cycles this is because it depends too much on things, but fundamentally half a nanosecond is about the fastest thing a computer will do. When you then, these are all inside caches. So L2 is another bit of the cache. It's just a bit, it's because caches have levels, but not really important for today. The key thing really here is like, you're looking at tens of nanos, like below 10 nanoseconds to do things from cache, really. Okay, below 10 nanoseconds.
This is one thing I'm learning with the Acceledraw is it can still pick up my pencil so much more that I cross out my. So you said single digit nanoseconds?
Yeah, single digit nanoseconds is your cache stuff. So everything in cache is single digit nanoseconds-ish. And these are mostly kind of like orders. Like the way to think of this is like, it often ends up being a bit like, it's a bit hardware dependent when you get down to these low speeds, like really fast things. So these are just, it's best to think in terms of tens of, hundreds of, single digits of for this stuff, because like, you'll get a lot of people go, well, actually, blah, 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 blah. And that doesn't really matter. For most practical use cases I know of, and nearly all the engineering I've ever done, including like hardcore, like handwriting the assembly stuff, an order of magnitude of time units is all you'll ever need in kind of resolution. It's only ever come up a couple of times when we talked about actual exact nanos.
Okay, now that we went through a bit of the beginning part again,
Mhm.
what would you say? So we talked about that cache is
Yep,
megabytes, and now we're talking
these
about
days,
that
yeah.
cache is nanoseconds.
Yep,
So it's how long it takes to process. It
to
takes
do something,
na-
to do something, yeah. Cache
nanoseconds to process.
actions, yeah. An action from cache takes nanoseconds. The reason I say action is because it's a bit vague when you get into the cache of what you're actually doing. And I'm trying. I'm like the general rule is, yeah, using stuff from cache is nanoseconds,
Okay, so cool.
and
And
then the next one
yeah,
up is RAM or main memory. So RAM, of course, is random access memory, and this is where I talked about the computers from the 80s because this is RAM was specifically is often specifically used to differentiate from ROM, which is read-only memory, or
oh,
EPROM and other things like this, where this is memory where you could basically what's known as flash it once and it would hold whatever you gave it.
okay.
And you could never write to it, but you could keep reading from it very quickly. So
Okay.
main memory reference, this is accessing something in your main memory is hundreds of nanoseconds. So you got a RAM for 100 nanos or more. So 3-digit nanos.
So this is random access memory, not read
Yeah,
access memory. Okay.
read-only memory. Yeah. So RAM, not ROM. ROM is not relevant in today's world of what we do. Uh, I wish I could say ROM has not come up in my career as a thing I need to deal with, but my career is otherwise known as I do nonsense.
Yeah, that's one way to put
So,
it.
oh yes, yes, people pay me for the nonsense.
Okay, see if this one's random. Okay, cool.
Access memory
And I think that's why I'm also getting ROM
is
is
read-only
read
memory.
only.
Yes. So this is a useful thing to know only because it will help understand the acronym, right? And the problem with this stuff is always that it's like the idea of there are people who think a floppy disk picture is just a save symbol, not representative of a disk we used to physically have. Is the like
Yeah.
there's a lot of problems with computing. Computing is now old enough that things have gone and it changes so quickly that things have gone obsolete that used to be so core to what we do that their names or their pictures persist so much longer than the actual thing themselves.
Yeah. Yo, what up, Lex? As you could see, I was probably way too focused on writing notes. And yay, Lex has been learning along with me. I found out yesterday that the way I explained Docker and Kubernetes in basic terms made sense to somebody else. I was very excited.
It
Um,
took me ages to get my head around like why that kind of virtualization mattered. Like I don't mean ages. Like it was like a couple of years into using it before I was like it finally clicked of why this was relevant.
oh, I don't, that like makes sense to me. But then there's like this kind of stuff where I'm like, why can I not get it? Um,
So I suppose I suppose this is the other classic thing of like this is where I started, like at this kind of level of like bits on wires, versus you
yeah.
started probably with more complete systems, and it's just all it comes down to is like your entry into this world comes from one side or the other side nearly always. So you either know some stuff, you don't know others because there's just too
I'm
much to know now.
I'm trying to think what SSD is.
Solid state disk.
Okay, solid state disk.
So this is
And
differentiated from the old hard disk drives, which were spinning because they actually used to spin, of course. So they don't spin because they're
oh,
solid. No moving parts in an SSD.
I've used to spin.
And this was kind of noticeable because if your disk was in a particularly bad state, you could hear it going tick, 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 which is the head moving around, the read head moving around, and occasionally hitting on the disk itself.
Oh, Lex, I am going to be starting a new database next month sometime, and I think I'm going to be building Raspberry Pis.
Yes, I
So I'm
actually
going to
have
have,
some of them here, which
yay.
we're going to be
And
using on for this.
Yes. So Lex, I'm gonna like need to make sure that you're like in the audience when I get stuck for those. Okay, cool. And I also put a few more notes of like solid state, just so that way I knew the difference. And I think
Yes.
something that I might have missed last time
Mhm.
was the fact that RAM erases when it's turned off, where
Yes.
solid state saves it.
Yes. And this is actually one of the more important distinctions. So there's a whole line I could follow about. There's it depends and a well actually, but there's not. That's not important today. What's important today is that like this is why a lot of tools like Kafka and Redis are often so things like Kafka are actually quite important because everything in Kafka, once you've got the acknowledgements back, have been written to a persistent disk, which is like an SSD. And where we work at Ivan, sorry, all of our machines have attached solid state drives. And so every time a Kafka message comes in and it's saved to that disk, it means it won't go away if the machine is turned off. So that therefore is what's known as a durable write. So this is where the terms durable often come in. So durable data means that it'll survive the machine getting powered on and off, whereas ephemeral data doesn't. So Redis is famously ephemeral most of the time
Oh.
because Redis is all in RAM.
Okay, this is not proper. You know what? I feel like it'll at least help me keep my memory when I get there. And I will ask you about what you just said in a bit because I
No
feel like
worries.
I could go to a tangent on that. And then we have, is this last one? I'm looking, I don't know why I'm looking on my tablet instead of
This
on my
is network
screen.
attached storage, really.
So like AWS.
Basically S3 or equivalent. So I just call this network storage, really, because
Okay.
it could be almost anything.
What? Okay, so networks. What? I just
Network
changed
storage.
you.
So these days, it's nearly always what's known as an object store, which is something like S3 or Azure Object Store or DigitalOcean has one. Did you just delete something?
Yeah, and I don't. Oh, I found my undo button. Thanks. Sorry. I was looking for the undo button. I got it.
No
We
worries.
got there.
So the point really is that like to make here is that like this is data on a different machine now. Right? That's why I always refer to it as network storage because to be honest, like it could be almost anything, right?
Okay.
But it's data on another machine, so network attached storage. So S3 is a magical thing Amazon have built to give us access to near unlimited storage. Then everyone else, of course, has their own equivalents. If you go back 5+ years, this would have been we do use something called HDFS to do exactly the same thing, but we'd have to run that ourselves. Classically, this was just a big, just a remote disk access to a machine somewhere far away. And the reason why this is important is like what we're now saying is mostly just how long things take. So if we go back at that kind of black, blue, green, and red, right? And a random read on your SSD was about 150 microseconds, right?
Hmm.
Now, let's say you're going to read something from a disk quite far away. So now we're 1,000 times slower to go to, let's say, to go from California to the Netherlands. And now what
Hmm.
happens is once we get there, we have to do the read, which means it's got to go through an SSD read, and then we got to go and send it back again. So you've basically got you're literally 1,000 times slower to read from S3 than it is to read from your local machine.
And okay, so that part makes sense.
Mm-hmm.
What are external hard drives considered? Like I
So
know they have some SSDs, but then they have HDDs.
HDDs. So hard to they might so an external drive could be anything in a box. Like, your flash drive, pen drive could be one of those as well. For all intents and purposes, it is a network attached storage device, except the network is very small.
Okay, that is
Like,
helpful though.
and so the main thing to
Mm,
understand here is I'd say a big reason that takes 150 milliseconds to get from one place to the other is the speed of light is only so fast, right? So literally the electrons take a little bit of time to go from one place to the next and back again. So if they've only got to go to your pen drive, which is plugged into your USB port, that doesn't take very long by comparison.
Okay, so totally getting this now. Now, so the network attached and like the external drive totally are not starting to make sense. I guess,
Mhm.
and I think this is going to lead us somewhere else of then where does AWS and those type of things come into it? Are they the same as network attached as
Yes.
like GoDaddy hosting server?
For all intents and purposes, yes. So, like, if we scroll a little, so I'm going to scroll to over to one of our earlier diagrams again, which is the one it's straight down, actually, just straight down.
Yeah.
So what's going on here, right, is the idea of you're loading data into your CPU from your drive, right, your SSD, and then you want to go to S3, so there's a network hop to a different CPU somewhere else, right? And then they're loading from their massive pile of much cheaper SSDs or tape drives or whatever else they're using, right? It doesn't really matter. They've got all their storage on their own machines, and they've got to load it, put it in their CPU, and send it over the network to you. Now, let's just say for a second we are, I don't know, downloading a file from GoDaddy, right? From a GoDaddy hosted
Okay.
web page, right?
Mm-hmm.
I say, give me that file. That sends a ping over, and then that file starts to download. For that file to
Mm-hmm.
download, the web server running on GoDaddy has to access the storage in GoDaddy, right? And then start sending me the file.
Okay.
All over the wire, right? So that's
Right.
some CPU operations. Then it reads from its SSD into its CPU, then blats it over the wire to me, and then it's read in over my network into my CPU, then written to my SSD, dependent on some stuff. But for all intents and purposes, that's what happens, right?
Right.
And the whole point here is S3 is just someone. Once again, this is the main thing about the cloud and everything in the cloud is it's someone else's computer, right?
Okay.
Or someone else's big pile of computers. Or in the case of S3, a comically large number of machines running in a comically large number of data centers with, frankly, ludicrous levels of redundancy, allowing you to basically read blocks of data at near random access surprisingly quickly. So networks attached data, and this is just a catch-all term I'm using because it could be anything. Like back in the day when you just hosted your own little web server on a machine somewhere, you might have a single U1 rack in a data center where you've literally walked up to the data center, plugged in your rack, plugged in the cable, and be serving from that directly. That meant all the data your website could serve came from that rack. But as a user, that's remote disk storage effectively, which you're accessing. So if you
Okay.
want to data from that server.
This is starting to make so much more sense.
So the golden rule here is that most things are weirdly the same when you slice enough layers off the top. The problem there's a lot of course very important details which we can politely ignore for today because genuinely they don't change much because fundamentally they have to work this way.
Okay.
Right? If you think about it, there has to be a computer at the other end. So I say, give me file X. And AWS has got to have something that says, I know where file X is. Here it is. So it has to be a computer.
Right. And that's all making sense because this is also starting to make more sense as we go into like yesterday, Anthony was on the show talking about Docker. So this
Yes.
is making a lot more sense with Docker as an example of whatever this red box is. Now, and this might be taking us off on a different tangent, but
No worries.
this is the fun part about Teach Jenn Tech. We kind of have a goal, and then sometimes we just go off on different
Yes.
parts. So we are taking it to the network, taking it off of the network. Why is it going from the SSD to the RAM to the CPU instead of vice versa?
Okay. So So this is merely because I drew it wrong.
Oh.
So if I correct my drawing for a second here. So this is merely because of the way I drew it. So what really should happen here is, if I can remember where my controls are, please keep the right settings, right? So let's draw this box, which needs a little bit of fill because the fill is really pretty on this, right? And let's call this, because this is where I get in trouble for oversimplifying things. So this is
I'm gonna move all this stuff above here. There we go.
So this is where the level of abstraction kind of comes to bite me. Let's see if I can zoom in. I can zoom in. There we go. So if I make this a bit bigger, I make this a bit bigger to go with it. So this is the network device. This is your machine. Your machine has a physical device which handles the networking for it, right?
Mm-hmm.
So if I want something from the network, right, I load it like this, right? Because it's a network device. Then this is going to probably go directly into the network device. Basically, goes via the CPU, like that.
Oh, okay.
So what happens here is let's say you start loading data on your local machine off the SSD. Now you want to load data off the network. So you go, CPU says to the network device, go dial S3 and give me some data, please. Mm-hmm. Or basically, if I has a GET request, and the GET request hits a video, right? Mm-hmm. So that goes over the network device to the CPU of the other machine and says, I want this video, please. It goes, okay, sending. Pulls it off the SSD pile at the bottom, right? And then loads that through RAM, through the CPU, it buffers into the RAM and sends that from the CPU through its network device to this network device, which beams it, and the CPU then goes, what should I do with this? Probably buffer it in RAM. And then once it's in RAM, I read it back to the CPU to play that video we were talking about last time around.
So,
because effectively your red box is missing, and what was missing previously is that red box you just drew for your machine. So if you draw a red box around all these boxes above loading over the network.
Yeah. Well,
because that's your machine.
So the words.
No, let's start with the red box because that actually simplifies things a lot.
Well, is the CPU the brain then?
Yeah, it is literally. It's often described as the brain of the machine. Everything goes through the brain.
This is helping. I think this is helping. Hold on. Let me draw this out to see if this is actually accurate. Brain. Okay. Yay. That's not. Sides.
1 second. Let's get this right.
So with RAM, if I'm watching a YouTube video, it's using RAM, but it's not going to the SSD because I never downloaded it.
Yeah, exactly.
Okay. I'm getting there. I am getting there.
And the reason why it holds on to it for a little bit is Chrome says, I'm going to hold on to that, even though you've just closed that tab, I'm going to hold on to that RAM for a little bit longer until 100% I'm sure you're done with it. So if you notice, I've just drawn a box around the outside of this, right?
Yes. Yes.
So this is your machine.
Okay.
This is the network machine.
The stored and browser cache, but that's not the same as CPU type of cache.
No, it's a cache. So this is the other classic problem of all the words that you use for everything. So a cache is, so the problem with, so this is where we normally refer to it as L1 cache or something like that. Because Redis is a cache. Your browser cache is a cache. Your SSD has caches built straight into it. There are caches everywhere.
Why?
And why? Well, because of what caching is for, which is that everything is slow, therefore we cache. As in, it's cheaper to hold the data for a bit, the data we think we're going to use next, than it is to try and fetch it again from the zero. So it's the other classic thing of why do we save bits of the web page? So why do we cache bits of, let's say we go to I don't know, LinkedIn like twice a day, right? So all the LinkedIn assets are actually saved in your browser cache, right? Because it's much better to hit a hot cache which has data in it, than it is to load it over the network. You could load it over the network every time, but then it'd be slow. It would waste literally tons of stuff. Like, why waste the power? Why waste the internet? Why waste the bandwidth? And why waste your time? So that's why we cache stuff. And it's exactly the same. It's like, why would your CPU not hold whatever it could in cache to act on that there and then before it has to go fetch another chunk at a time? So caching is basically picking up, it's the idea of saying, I'm going to pick up a carrot, take it over to the bench, chop it, and then I'm going to pick up another carrot, rather than going, I'm going to pick up 5 carrots, bring them over to the bench, then cut them up. Because my cache is my bench space is enough to have at least 5 carrots in it.
Okay.
It's stopping round trips. Caching is all about reducing the number of round trips you've got to do, because most things happen more than once.
And this is making sense. So is cache the same as buffering then?
Yep, that's the same thing. A buffer could be called a cache.
Sweet.
Quite literally.
I am putting 2 and 2 together now.
Yes.
So
in fact, I'd go one step further to say a buffer is a specialized single-purpose cache.
Oh, okay.
Because a cache can be anything, but generally, if you buffer something, you're buffering one specific thing.
Buffer.
Whereas a cache can have many different things in it.
Is a cache.
This might be a semantic argument you might cause, though, but I will happily stand by that for now until proven otherwise. If I'm wrong, reach out in the comments.
I'm asking because this is making a lot more sense in the fact that now when I go back down to my examples that I was working on, like reading earlier, it's making a lot more sense how we're going from place to place and what places are used for. This is oddly, I think a lot of it had to be like you had to go through this the first time, last time, and then I needed to go through the same stuff again to ask more questions because this is seriously helping. I think
so.
Oh, go ahead.
No, so this is kind of to go back to the database thing. Is like, so Postgres cache is built into it. So if you do a query in Postgres the first time, it takes a long while. But if you do exactly the same query immediately after, it doesn't take anywhere near as long because it's still holding the result.
And when we talk about query, are we talking about like if we go to the Spice Girls example from the last episode, let's say we are looking for things with Scary Spice.
Yes.
Would it be considered the same query if I look for things with Baby Spice?
No.
Or is that a new query? Okay.
That would be a new query. So let's say both you and I were looking for songs by Scary Spice. So my query landed first. It took 4 seconds to come back. This is an arbitrary amount of time. It's just an amount of time, 4 seconds ago. That was slow. However, you then queried after I did and asked for exactly the same thing, songs by Scary Spice, please. But because there's a cache in there, it goes, someone just asked for this. Here is your answer. I don't have to go search for it again.
Even if we're in different locations?
Yes, because it's the same database.
Interesting.
So that's what caching is all about, really. The idea of caching is to say the same thing. It's very rare that things happen exactly once. It's quite common things will happen more than once. And in a lot of cases, the same thing tends to happen over and over and over again, right? Now, we have a lot of tools which are optimized for these various what's known as access patterns, right? And access patterns really determine what tool you use in a very real way. So whether you need to keep your data in RAM or can you keep it on disk, depends how you access it or why you access it. And this is where like everything from your database choice to like how you build it matters.
So
So if you think about some data of like, let's say back to the video, I want to access this video, right? Well, it's probably going to be a big file. It's going to be stored in chunks and I'm going to keep it on my disk, right? And I might have a little index file that tells me how far along that video to go to get to, let's say, the chapters, like chapters in the video or the key points in the video. But fundamentally, the video doesn't make sense unless you read it in order, because it's a fundamentally time-ordered thing. So the only way you search it is time, really. in video. But back to our discography, right, of the Spice Girls, there's various things we want to search on, but also it's very likely that the amount of data you want from that thing is very small compared to the total amount of data. So you want to be able to query and get a bit back rather than saying a video where it's very likely you're going to watch all the pixels in the video.
Okay.
Think about it.
Yes, I feel like I just wrote this down. There we go. Apparently it's going to be giant. That's cool. So when we talk about a floppy disk or a CD, I don't know if external hard drive goes with it.
Yep,
Would
probably
those,
does.
I get they're technically network.
I would consider, for the sake of this, we're going to consider the network attached, because fundamentally there's a wire going from your machine to the device, which then has to read something.
But they don't use RAM because they're not randomly erased. They use
There are file storage. So this is where the term here is a storage media.
aha. Okay, cool. I'm still gonna put it in red, but
We're good. No, it's always good. So the different storage medias you have are things like a floppy disk, a CD, an external hard drive is just a hard drive in a box, or a flash disk, like your SD, like an SD card. These are all the same kind of thing if you think about it, which is a device external to your machine which stores data for you. I consider them network attached mostly because it's a very convenient way to term these pieces of tech. They can, as per always, analogies start to break down when you get into specifics, but if you're ever using a floppy disk, it might as well be considered network attached for the speed.
fair enough.
I still have a floppy drive, which is quite fun.
I had to go buy an external hard drive or external CD driver because
Yes.
health tech is not up to date with the rest of the world. So when I go get my MRIs done, they give me a CD.
Ooh,
Or I have to wait like weeks before I get the results back. So
I can believe that.
yeah, so I went and bought one and I'm like, well, now I have it. So I think this is
Yes.
also really helpful. Again, gonna go a totally different direction.
Always
It's
good.
so fun. It's so fun. Okay, so we have file storage media, which this makes sense when we talk about these devices and we talked about Spice Girls, all that. What doesn't make sense now are projects like I want to build a Astro website or something because they all start with one folder and then
Yep.
they are a file storage and they have structure.
Yep.
I
Okay.
guess I'm not like I get it, but I don't get it going from A to B.
Okay. So you're in that weird kind of space where you see your project directory, which has all your files in it, right? And what happens next? So the key thing really here is what your machine can. So this is where we actually hit the other path. So there's more than one way things work in a CPU, just because of nothing can be simple because we're not allowed nice things.
Fair
No,
enough.
it's not too bad. So this is where if you learned to program in the like the 90s, you would have been taught this first, and you would have been wildly confused at the time because that's how they taught programming back then.
Okay.
It was very frustrating, which is the idea of the program counter versus the execution stack. So what's going on right now is if you imagine you've got your Astro files, the first thing that happens is we're going to assume there's a program running, right? Which is the interpreter. Your computer goes, I will load this file into RAM, then it'll throw it into the node interpreter, it'll chew it up and spit out a series of what's known as intermediate representation, which is just another file with a very different shape. And then it'll basically follow the instructions written in that file, right?
Okay.
Basically, you load it, and then what happens is all the different function calls you've described, all the different states you've described are turned into executable code on the machine via this program called, which is the interpreter. What happens, the important thing to note is that like you have all this project structure, and fundamentally, why the structure is mostly there to make your life easy. It's not to make the machine's life easy. What the machine does, it takes all your files and all your folders and munges them all together into one blob. I kid you not. That is normally how these things work, right? Because fundamentally, the machine just tags these as a series of objects in what's known as an abstract syntax tree, where it basically builds a diagram for itself. A diagram is not really right, but it's basically a diagram of all the blobs in your code and all the flow paths, a massive flow chart, right?
Yeah.
Of all the various states your machine, your system could be in, and then how to get to there, from there, from there, from there, from there, right? And then you say start. It goes to the first box, which is your main function effectively, and it says do this thing. Now, with Astro and tools like that, there's a whole ton of extra code which is loaded behind the scenes in the library that makes Astro work, right?
Okay.
So if you imagine you load, so it's actually a bit easier. It's easier to start this from a different language than Astro. Astro is about as far removed from this.
Well, really quick, for the executable, like, and it reads it, is that just the OS, and is that part of the CPU?
No. That's, I wish, but we're too far. This is a problem. So we are a few levels up from that. So what's happening is if we scroll back a bit, that a lot of like more simple programs are written in C, where you remember in C you have like int main and then some stuff, right? Right. So int main, and then just say printf hello world, right? And then you close the braces, and that's it. So that little program there gets compiled down to machine code effectively, which is what your executable is, right? Executable is machine code, which you basically, when you double click on it, that gets run by the OS says, I know what that is. In Linux, that's called an ELF binary. In Windows, it's an exe file. In Mac, I do not remember the actual extension name anymore, but a DMG, I think.
Yeah, I think you're right. I'm pretty sure it's DMG.
Yes. It might be. I can't remember. So what happens next is that the OS basically says run to that executable, right? And it basically starts feeding it to the CPU via the instruction cache, which is another cache. We've been talking about data caches so far, but there's another one called the instruction cache. Right? I know, it's annoying. I was hoping we could avoid that. But it doesn't really matter.
Now that I know there's a ton of them, it's starting to make more sense. So we're good.
So if you imagine there's two tracks of things flowing through the CPU. One is the instructions saying do this, do that, do this, do that. The other is the data of things to act upon.
Yeah. Okay.
Right. Cool. So that's what your executable is a series of machine code which goes in the instruction cache, and the data it needs to operate on goes in the data cache. Now that's kind of like on the metalish stuff in C. Now, in your Astro example, what happens is there is a piece of code that does that, but it's a lot bigger, and it's called your interpreter. And what that does is says, most people don't have time to write all this stuff out in C or equivalent languages or Rust, and says, the assumption is that we'll give you a different language to write in, which gives you more powerful objects to work with and more flexibility to work, which is, you can write 4 lines of node code, which would take 1,000 lines of C to write, because someone's already written 1,000 lines of C behind the scenes for you.
Okay. Oh, it really is pretty behind it. That's sorry. That was getting distracted on how pretty it actually is. That's fine. So I'm just thinking if I download something. So this came from maybe I don't want a background and I want block, please. So let's say I downloaded, what am I going to, Spotify. We're going to say Spotify because that's where my mind's going right now. So it downloads, and this is a network access. Blah, blah, blah. And then it downloads, and we go to having another box. Sure, we can have a black box. That's fine. And so when it gets to the box, it is sent to the CPU, which, give me a second to see if it goes to the right mindset. But then it goes to an interpreter, interpreter, which then moves it to a, and then it runs the program?
So the interpreter basically is another piece of code which runs other code. It effectively says, I follow instructions you've given me, written in a different language.
So this is
Yes,
where
basically.
you do like
So
JavaScript.
yeah, JavaScript, Java, Python, Ruby,
Okay.
C# in most cases. All this stuff
Goes through the interpreter,
yep,
and then
and that drives the CPU to do things.
so
Like
it goes
I
through
say,
the CPU to tell it to go to the interpreter, and it goes back to the CPU.
so no, it's basically the interpreter is a special program that just executes what it tells it to do, but it's on the CPU itself. So let's just say yes for
Oh,
now. It's basically an alternate. Like if you imagine your operating system runs the C code is basically telling your operating system to do things. The interpreter is that piece of C code, your JavaScript telling that bit to do. It's like an extra layer. Imagine like you're wrapping things up.
okay. Okay. I feel like I can pause on this one because it's at least giving me some idea
Yes.
of how to start conceptualizing it.
Yes.
Because trying to figure out how data works is very complicated, I have
Yes.
come to realize.
Yes. So the problem here is that, like in a lot of ways, what we do these days is quite far removed from the PDP-11 model I mentioned earlier, which is how a lot of people think about programming and was taught programming because we're old. And where this gets interesting is if this stuff is when you take it from the other side, when you build it up incrementally, you end up with a kind of more complete picture of everything. However, it takes a very long time, right? As in, there's just tons of frankly useless information in my head now for systems that no longer exist and for ways of programming that are no longer relevant.
But they help me learn, and so many
They
others
are quite good
learn.
fun.
But I will say now that I have completely derailed us, and we didn't end up going to Spice Girls this time, I'm not
Not
sure
today.
where to go from here.
Well, a
'Cause-
logical answer is definitely to a rival girl band of some description.
okay.
No. I can't honestly. I think. Oh gosh, All Saints was around at the same time, weren't they?
I don't know.
Problem is, this is where the problem with Spice Girls is Spice Girls were international enough that everyone knows the Spice Girls by comparison to almost every other band I can remember from the Britpop era.
Well, I mean, you mentioned NSYNC last time, so we can go with NSYNC this time.
NSYNC will do nicely, right?
Let's talk about NSYNC. And for this one, I am going to. Do you want to share your screen since I know that you're going to end up showing us stuff, or do you want me to continue and just scroll to wherever you need me to scroll
It's
to?
probably best if you keep scrolling, mostly because
Okay.
my screen is doing something strange right now, and I forgot to turn off Slack, and now and people are messaging me about things which are neither important right now, but things I want to make sure I have an idea of how to reply later. As is the case of everything.
Okay.
Also, I have too many tabs open. My computer's running a bit slowly. Okay, cool. So the key thing is if you scroll back if you jump to where my mouse is by pressing, so there's a little button in the top corner where it says like just the B on it. Just hit the B.
Yay!
It'll
that
jump
was
to
fun.
wherever I am.
Okay.
So if we start at this point again, so now what we're going to talk about is we're going to deal with the NSYNC discography, and we're going to deal with the fact that the data is now we're trying to deal with data which just keeps growing. So we're actually, we're now Spotify. We have NSYNC. The NSYNC discography is a very popular piece of music, right? That's actually not that large, the total file. You've ripped a CD years ago, a few hundred megabytes. So that's not too bad. You could feasibly have that on your machine for a single CD. But when you have, let's say, a band which is very prolific and has literally 30 albums, it starts to get a bit large.
Queen,
yeah, my gosh, Queen have a lot of albums. But then what happens is you think about how big is your playlist, your default, I liked this playlist, right? A few thousand songs?
Yeah,
a few thousand
probably.
songs. And that's where it gets a bit difficult because it's just a bit too big. But these are all the same, so they're not too bad to store. So you just stream them as you need them and you cache the ones locally. But now you're actually Spotify, and Spotify behind the scenes has a record of everyone who's played any individual song, because that's important, because that's how they pay their artists. So they need to know that Jenn played Bye 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 400 times last week, right?
Wow.
Yeah.
Yes.
And they need to know
Yes.
that Ben actually likes the Backstreet Boys slightly more. Shock horror. I
Oh my
know.
goodness.
I know. Right? And so this is where like these kind of numbers are really important, because that's how they pay the artists and deal with licensing things. So what happens is, over time, the data of who did what and when grows bigger than the songs themselves, right? So if
Okay.
let's say they have a petabyte of music, right? Which is a lot of music, and potentially they probably have more, but let's say a petabyte of music. They can store that they probably store that in multiple locations, so lots of people can read it at the same time. So it can be nearby people and also read lots of times. But they probably have one or two very, very large databases which have replicates of all the data of who played what. Because I listen to Spotify, probably close to 10 hours a week.
Yeah.
And most people I know probably do something similar. So
Yes.
every single one of those clicks is another hit on their database. So their database is probably tens of petabytes by now of their playlist things. So that's way too big to fit on any single machine by a very, very large way. So what happens now is you think, I need to access all that data, right? I need to have, and the point is all that play data, you very rarely need to know who played a song at what point in time exactly once. So this is where we get back to access patterns, because I only care about play data in aggregate. I only care that you played XYZ number of songs, or how many times was Bye 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 played by people, or by people in America, or by people in New South Wales, in Australia, that kind of stuff, right? Like I care about, a few small things with small piece of detail. So this is all going to be loaded over the network. So you only care about moving what you should. So if we scroll to where I am, which is up and to the right, to this column versus rows data, right? So this is where we have all that columns of data about all the plays. And this is why we use column stores, is we only care about one or two of these columns at a time. Like all the plays, please, for, I don't know, give me all the plays by Jenn. So I'm going to filter on the first column, which is who played it, and then on the third column, which is what they actually played. So I now have all of your plays at any time. So you can now scroll back through what you played, when, and where. Now I want to do a thing that says, give me all NSYNC plays. So the second column is the band, and so every single line is a play. So all I do is say search where column A equals NSYNC. Pull them all out, and I pull out all the durations, which is another column. So I only pull these two columns at a time, and now I have total duration that NSYNC gets paid for. So this is why we store data differently, because the access matters. If I store this in Postgres, where everything's a row, right? Every time I pulled out data, I get the whole row every time I accessed it. Which would have the useless data at the end that says the metadata, like where you were when you played that song, which I don't need most of the time, or which device it was on. Very useful for some people who are optimizing for playing on phones versus Alexa devices, but not very useful for just how much we have to pay NSYNC. And if you imagine that these rows, there are, let's say, 400 columns, right? Going sideways, there might be hundreds of columns. If you imagine I had to pull hundreds of columns rather than the one column I actually needed, I am wasting time.
So that is making sense. Would you say that it's easier to sort with column type
Yes.
database because you
Column,
can
so the reason to use column
filter?
databases. So it's filtering through so column databases are optimized for the simple fact of, if you need aggregates where one column is deciding what you do in some way, it is nearly always much, much faster, potentially multiple hundreds of times faster to go through a column than it is to go through a row store for this stuff, right?
Okay.
But also, caching tends not to work very well on these, because on average, what I want to know about the NSYNC plays and what you want to know about, let's say, what mobile device someone's playing on, are two entirely different queries. So you don't really cache column databases very often.
Okay.
So if we flip it around to instead say, I want to store playlists for Spotify, right? So I need to store them somewhere. They'll probably be in a database somewhere. They might even be probably in something like a MongoDB type storage solution, right? Now this was where caching is good because they know that Ben loves to play his morning playlist every morning, right?
Mm-hmm.
And I only really use 2 or 3 of my playlists all the time. So the cache they'll probably use for me basically only has those 2 or 3 playlists in it, and they know to retrieve them very quickly. They also know that the playlist being shared by a big social media influencer is very likely to be hit lots of times. So they'll store that in something hot cache, some hot cache. So that will be cached somewhere in RAM rather than on a disk, because they don't want to read the disk every time to get that thing that's going to be read literally 100,000 times a day.
Right.
The example isn't really holding up at this point, but it's hopefully the kind of the gist is getting across, which is that you store stuff where it's relevant. So if it's a small piece of data accessed every time, like regularly, you'll keep it in RAM somewhere. If it's a random aggregation where it'll change quite differently every time, like I don't need to know the same thing in every analytics query I do. You need to have a setup where you can actually just access all this stuff and then just slice and dice through the data quickly.
And that's making sense. I feel like my mind is going what's out of this area. Like, oh,
Go
this
on.
is making more sense of why a playlist that I play often, if I'm driving somewhere and I lose service, it will still play even if I don't have it downloaded. Where
Yes, because it
one,
knows it exactly. So it has an intelligent on-disk cache, by the way. So Spotify actually stores quite more songs on your phone than you might think, because what it says is it knows you happen to love that particular album by that particular band, and you play those songs all the time. So it'll intelligently say, "I'm going to store these here for now," and every time you play them, it resets the timer before it deletes it.
okay, and
So
that's totally
yeah.
making sense.
So let's say it says I need an intelligent cache of the top 100 songs Jenn plays, right? But if Jenn doesn't play a song for 10 days, let's say, I'll throw it away and replace it with the next most popular song.
Okay.
So then what happens is if you do play, let's say, top 20 songs over and over again, they're always on your device. You can always play them, right? They'll always just play immediately next when you hit hot to them. There's no loading time, right? But now you load that. Now you want to add one of those brand new songs you never played before. It takes a second or two to Spotify to link up. You'll notice it if the Wi-Fi drops out. But then you go back to an old favorite next, and it's immediate, even when the Wi-Fi drops out.
Yes, and that makes sense.
And this is like smart caching. So and once again, it's caching because if you're storing an arbitrary number of things, but nearer to where you need them.
Okay. That's making sense. I'm also over here writing down that someday we're going to definitely need someone on the show to talk about all the caching in the world and what is caching and what are they used for. And
so this is an interesting one because there's a famous phrase about programming and then a joke on top of that, which is there are only 2 hard problems in software engineering: naming things and cache invalidation.
naming things is always a problem.
And then the other one is caching. Basically, that is considered the second hardest problem in programming.
Yes. Yes.
And I'm not actually joking. Caching is genuinely one of those areas of like actual hard engineering, though it is yet another one of those ones where, like naming things, you can get away with being pretty okay at it for a very, very long time.
And I feel like now knowing that there's different types of caching is also making a lot more sense with all of this, because I kept thinking of caching like browser caching, but being able to break it down to why browser cache is different and why browser cache may disappear. This is all like making so much more sense. This like
Yes.
area by itself, I'm like, okay, cool.
So
This
it's all the same. This is my favorite line of everything is eventually the same, which is it's like fundamentally like you're accessing stuff in your browser and it's caching it locally, so you don't have to go over the network to go get it, right? The
Hmm.
same way as your video is buffered in RAM, so it doesn't have to go back to your SSD to read it.
Hmm.
And it's exactly the same principle. It applies all the way down to your songs on Spotify, to the way why you use Redis in front of a database, to why you your CDs used to skip when you used to hit them.
I feel like I have more questions about this, yet at the same time, it kind of needs to sink in because I'm finally starting to understand the data side of it.
Yes.
Yet, I think something that would be cool for us to talk about sometime would be like, how is data created? Like, I almost want to find
Yes.
you or someone else to come on and be like, let's talk about the history of data. Dan
Ooh.
Moore has a amazing talk on the history of security. And like he
Mhm.
talks about how like at one point there were two tribes on each side of the river and they one tribe realized that they like call the river it's the same name but one says it differently than the other, so they knew that there were imposters when they said the river wrong.
Yes.
That is a very
So,
simplified version,
oh
but
gosh.
knowing
Yes.
that had my interest way more into data or into security because I'm like, oh, that's how we actually got there? Huh.
Yeah. So data and data storage and data access patterns goes back a very, very long way away as well. So you think about things like the Dewey Decimal System, right, of libraries, right?
Oh.
That is an early example of an index, a perfect index symbol, a way of sorting data and indexing data for rapid access. Because you
Yes.
don't know where the book is, but you happen to know already that the book is of a certain type. So you know you want to look at
Hmm.
botany. So you know the code for botany. You can go to that section very quickly. So it gets you to the right place to start looking. And as
Yes.
you go back in time from there, you find like that's actually quite a sophisticated system. Earlier ones, things like author name, very straightforward,
Hmm.
understand, or genre in a library is often another thing. But if you go back into things like record keeping and then things like the I can't remember which area of Italy the double entry accounting started, right? Because this is the idea of you map payments in to a payment out or a payment out to a payment in every time so that you could add up both sides of the columns. And if they went to zero, you knew you hadn't missed a payment.
Huh.
So this is why data was often stored twice in account. This is why data is always stored twice in accounting method. This is about 600 years old now. So we've gone back a few hundred years again. And this is like data storage. These were in books because these things had to be then transported by secure couriers between places. So that if you borrowed money from somewhere or put money in one place from one place, you had to go back from the other place. Because basically the book was the ledger that said, actually, we can give the King of France money today. Because we know he deposited money when he was in Paris, and we can pull it out when he's in Naples. And that was done by a courier, transferring the data to know that the money was allowed to be shared.
Interesting.
And my favorite thing here is back to the security thing is it was done by people with very carefully known handwriting.
Interesting. Yeah, there's so many different types of security that I
Yes.
I found his talk so interesting that I had no idea that much went into it, and to be able to talk about it now, um,
Security is such a huge field. It's ridiculous
it
because it goes
is.
back. It's one of those. It's also a truly old field. So data is a very old field as well, but in a lot of ways, its sophistication, um, how sophisticated it is, goes up and down over time. Like there are times when no one cared, particularly.
Hmm.
Like there are cultures where your birthday doesn't matter because you were born in a season. That's
Oh.
the precision, the level of precision they'll work to, right?
Hmm.
There are other things where um, things where the exact number of things you own isn't important for various reasons, or things are collectively owned. Therefore, ownership is not direct. Some things are collectively owned. Therefore, no one would have knowledge of exactly how many things there were because everybody might have them. Who knows where they are, right? And then when you get to places where particularly like if you look into things like the ancient Egyptians had a lot of data storage in like tablets and things so that they could have a more complex economy. But their economy was still barter based. But when you get to money, money then accelerates this data boom. And the Romans had great details of things. They still didn't have the concept of zero though. So owing people money was very strange.
I feel like you just, you/Dan gave me a great talk idea. Now I want to go research of how data became data,
I
the
would
history of
love to
data.
hear that done because it's one of those areas where I have a lot of bits of knowledge and no through line through any of it. It's fascinating. The double entry accounting thing is fascinating because of so I met a guy called Joran Grief recently at a conference I was at. I've been following him for a while. He's building a database called Tiger Beetle, which is open source and written in a language called Zig, which I'm a fan of. And it is a database specializing in accounting. And double entry accounting is a fundamental principle in the database. Because if you think about it, most accounting systems are just done on top of databases built for other things.
Mm-hmm.
And this one's actually like double entry accounting is literally a core piece of the system, which gets two interesting things. The first is you get double writes, therefore you actually have more data protection than you might think, but also it automatically keeps storage in the way that accounting rules require as a file format, effectively, which is quite special.
Interesting.
He
There's so
actually,
much.
I'll see if I can get him to do one of these with you. Actually, he'd be
Yeah.
a really excellent guest.
Yay, that would be amazing.
Yes, he gave an absolutely amazing talk on how data is stored recently at the event QCon where I was at, and it was amazing. I was like making furious notes and tweeting along because like it turns out there's a lot more things going. Like you actually have to start writing data to disk, and when you write it to disk, and how it's written to disk. Like these things, like because we've gotten so far along the journey from the older, computers designed in the 80s, like the abstraction level we've got to, even just in our operating systems, are so high that things aren't as easy as you think. And until relatively recently, Postgres wasn't as secure at writing data to disk as people thought it was.
What is his name? Do you remember?
I can find it for you, Joran Grief, but it's yet another ones where my
I was just
ability to
gonna
pronounce
say,
versus spelling is never straightforward. So let's
yeah,
just find
I
it.
was just gonna say, can you link the video if the video's out yet?
It is
For
behind a paywall, so
oh, just kidding. I mean, let's
uh,
link it anyway, because if others want to pay to view it, we should probably at least
so
let them
here
know
I'll
where it
show you
is.
his Twitter profile.
Perfect.
I'll just ping you on our Slack for now, and we can go from there. I'll ping you on I'll intro you on Twitter or something on LinkedIn.
Yay. Perfect. Well, then oh, hey, we follow each other.
It's a small world.
It is. It really is. I always get really excited when this happens a lot when I'm like, I follow them. They follow me. This is fun. When I had
So
no idea what they do and all that.
we took a picture together at QCon, and then a mutual friend of ours
Oh,
reached out immediately to both of us saying, "Hey, you know so and so?"
yes. Yes. That happened yesterday because Dan Moore was on my friend Ramon's and Rozelle's show where they do CFPs and talk practice. And so I was like, wait, y'all know each other? That is, huh? I did not realize that. And it's so fascinating. It's such a big and small world all at once.
It really
Yay.
is.
Yay. Cool. Well, I will say that I'm probably a little I don't want to say frazzled. My brain is starting to be full. So I have a lot to work on. I can say that. And there's a
You've entered
lot
disk
more of a
swapping mode.
yes, I need to disk swap. It
So
has
that's
been
actually a thing where you run out of RAM and you need to swap. You're doing what's known as swap disking, is where your RAM swaps in and out of your hard drive. So actually, you're storing things on the hard drive because you're out of RAM.
oh, so you move it from the RAM to the hard drive so the RAM can
Yeah,
erase itself.
yeah, and be reused because it's not being used right now. So if you ever run into a swap disk thing on Windows, that's what it's talking about.
This is a very silly way of it's not Windows, it's on Genshin Impact. It says the CD switching.
Like that, yes. So when you run out, so the funny thing here is there's a really, really good video I will share, and I recommend you share to the crowd, which is talking about the original Crash Bandicoot game, right?
Oh, I love Crash
Because of
Bandicoot.
disk streaming and all the tech that does all that stuff and caching, live caching off disk, was invented by the Crash Bandicoot team in most cases.
Oh,
Because of, you remember how much better Crash Bandicoot looked than every other PlayStation 1 game for the
yeah.
longest time? Like, so much better, right?
Okay, this is. Do you remember an IQ Cube game on PlayStation?
No.
There was like a cube game where you were a little human and you had to guess what cubes were gonna fall
Ah,
towards you.
so I didn't have a console in the PlayStation era. This was back, so I went in and out as a PC gamer. So I used to have a Famicom in the SNES era. I had a Famicom, an actual Famicom, because we lived in Pakistan for a brief period of time, and it was what we could
Mm-hmm.
find. And then later, when it came around to the PlayStation era, we were mostly PC gamers, and we got a PlayStation way deep into the middle of the PS2 era because it was secondhand. And
I
that's the other classic thing of we wanted to play Final Fantasy, me and my brother. So we
I
played
feel
Final Fantasy VIII so much.
that makes sense. And IQ Cube, I used to try to Google it and I could never
Mhm,
find it, but either my Googles have gotten better or Google
mhm.
is starting to learn what I actually mean instead of what I'm typing, which I think it's
Yes.
that because, well, but I found it. Oh my
Oh,
gosh.
wonderful.
I don't know if it's available anywhere, but I will share my screen briefly because look at it. I'm so excited. Let's see. It's this game. I don't know why it was so entertaining to me. I would play this stupid game for hours.
So I didn't
Hours.
know this was the original because I've seen so many people trying to recreate things like this in so many of the gaming like forums, subreddits I'm on. I did not realize there was a PlayStation game they're trying to imitate.
This game, like
Mhm.
I I love this game. This game is everything. And I should actually see if there's a way to play it now because
Yes.
well no, I'm gonna say I probably shouldn't because I will waste way too much time playing that.
So the video I've linked
So
to you and I recommend sharing because this is a genuinely brilliant one is about memory constraints and disk constraints on the PlayStation to the
yay.
point of where they filed patents for the technology they found.
That's so cool.
It's
Okay, I'm
like
linking
it's
that
because it
here
was
as
so
well.
short and like so loads of PlayStation games had very small levels by comparison to Crash because Crash could stream levels whereas they couldn't.
Mm-hmm. That
Which
is
is why Crash Bandicoot
interesting.
looked better than every PlayStation game for like
It
for the first
did.
3 years of PlayStation. It was like the best looking game by a really long way. It was
Yeah.
still good looking even by the end of the era.
Yeah. But Crash Bandicoot and Spyro, I don't think that they were made by the same people.
I don't know, but
Spyro,
Spyro holds a special place in my heart.
because Spyro had pretty good graphics too. And I
Yes,
think it
so
was around the same time frame.
it was. So I don't remember. So this is, by the way, this is like early Naughty Dog as well. So the people who made Last of Us eventually were the people who made Crash.
Okay, so Crash Bandicoot came out in now it's not telling me.
1995, I think.
Um History 1996 and
Ooh, not
Spyro first released in 1998. So yes, around the same time frame, but I wonder if the technology went to more programs within those 2 years.
it probably did by that point. So yeah, so they were by Insomniac. Insomniac were another like pioneering studio anyway. So they might have had some of
Mhm.
the same people, to be honest.
Yeah,
It's
it
hard to
was
tell.
definitely. I still have it. I downloaded it for my Xbox. They have it, and I'll play it for a while. It's definitely. I was always more into those, except Mario 3 and Mario
Mhm.
2. Those
Okay.
were also my go-tos.
So I definitely played Spyro quite a bit. I was always more of a PC because I played PC games mostly, so I was stuck
Yeah,
into Command and Conquer Land for a very long
yeah,
time, and things like Shogun, Total War, and equivalent like that. I mostly played a lot of RTSs.
yeah. A
um,
few of the D&D crew that I'm a part of, they want to start playing like what is it called? SC2, StarCraft 2. There we go.
StarCraft 2, yes, I still play
And I'm
that.
like, strategy games. IQ thing, I'll play it all day. Strategy games, I'm like, this no. Or,
So
or first
genuinely,
person
like,
shooters.
I don't play those anymore. My eyesight's too bad these days. But I play a lot of strategy games. I actually got a job once by playing Age of Empires with the company founder, pretty much.
Oh wow. Oh
Yes.
wow. Okay, so oddly, this does come to another data question. So this is
Hmm.
fun. So back in the day, like the
Hmm.
2000s, that's not even
Yep.
back in the day,
Oh, it is now,
having
sadly.
c computer cafes. Like you would
Hmm.
have to bring your own computer a lot of times to go play a game against your friends
Yes.
on the same LAN internet.
Yep. There's that same LAN, yeah, local area network.
Okay,
Yes.
so it would still be like an external or a network
So
access.
not really. So LAN gaming is comes from the era of you all had the same game, you all installed it on your own machines, right? Every single machine had a copy of the game, right?
Hmm.
Now, how game networking works is worthy of the whole chat on its own. I have a
Yeet.
talk out about this actually. Or I gloss over the details to explain it in relation to other things, but the key thing really is that fundamentally you don't stream the whole game from one person to another person very often. Normally what happens is you and I have the same game running on our machines with all the same data in it. What happens is if I say move left, I send you Ben's character moves left.
Okay.
And on your machine, you go acknowledged. And Jen's character picked up a brick. Acknowledged, sort of thing. And what happens is behind the scenes, the game software running on each of our machines synchronizes its state between each other, dependent on exactly how the game is being networked. That's normally what happens. One person is the authoritative leader of the game, or one machine is, and effectively all updates of the game are agreed by that machine and then streamed out to everybody else. And we just share the tiny changes
Okay.
so we can change it, so we can share them as fast as possible.
Okay.
So an example of how it can take a while is if you've played Minecraft and you join a new world you've never been to before, and people have done a lot of edits, it takes ages to load up the map, right? That is when it's streaming all those bits over the wire.
Okay.
Or VR chat does this as well. When you go to a new place and you have to load up the whole new room and it's big, it takes ages for it to stream in.
I'm also listening while trying to draw a computer that's not going very well. Um, because that's a very useful part of it to draw land, which, okay,
Yes.
this does make sense and why you would have a primary computer as well.
Yes.
So, a lot of things to look into, and
Yes.
I will also add that to my notes of
Yes. Game networking used to
ideas.
be my job for a long time as well. So like it's one of those things where it's like it's one of those areas which starts off deceptive. It starts off in a deceptively straightforward place, but rapidly becomes about dealing with the eccentricities of how weird people are and how weird the computers are, and effectively faking everything you can get away with.
So I think this is just decided. You will just be on the show every so often for forever. Thanks, Ben. You now we have two Bens on the show often. This is going to be fantastic. Yay! Because Ben Myers talks about accessibility a lot, and it's fantastic. I should send you some of their content. I think you would really like it. If you
That would
don't
be
follow each
fun.
other on Twitter, you should. Um, but yay. Okay. Well, this will wrap up for this week. And I know with my progression with Postgres and all the databases, I will have questions by next time. at the moment. Switching disks. Is that what it's called?
That'll do. You'll swap it. You'll activate your swap disk is what I'm saying. So swap disk. So
Swap
yeah,
disk.
you're moving memory. You're moving memory from RAM to disk, so you can do other things for a bit.
It's like sleep.
Quite literally. So when your computer goes, so this is what Hibernate is, by the way. You know when you hibernate a laptop,
Yeah.
right? It literally saves all the RAM to your disk, and then loads it all back again when it wakes up.
But it's like human sleep.
Human sleep is really weird. Like, the more I read about sleep, the more I'm like, this makes no sense.
Interesting. Well, on that note, thank you everyone for joining today. And please put down in the comments what questions you have. You can follow both of us on the Twitters as well as find us on LinkedIn. Mastodon. I'm on Mastodon. Are you on Mastodon?
I am. I'm on Hackaderm. I'm Ben Gamble 7.
Me too. Me too. But Jenn,
so same handle.
Not.
Yeah. So yeah, same handle on both because I am incredibly lazy when it comes to handles.
Yes. And thank you everyone and bye.